Alright, this video is gonna be the last video of the MLIR series, multi-level intermediate representation. That's what MLIR stands for. And I don't know why, but I took quite a long time to finish this series. So for this video, we're gonna start with going through the paper and scan the paper once, and after that gonna keep reading from where we were reading, which is parallel compilation, I believe. It's gonna be over here. Yes. Yeah. Okay. So MLIR, it's a new technology by Chris Ladner and a very crack team in Google. It sits on LLVM. The programming language Mojo uses it, or will use it, but this was, I guess, originally a project in Google. Yeah. Alright, so let's go through the abstract one time. This work presents MLIR, a novel approach to building reusable and extensible compiler infrastructure. MLIR addresses software fragmentation compilation for heterogeneous hardware, significantly reducing the cost of building domain-specific compilers and connecting existing compilers together. MLIR facilitates the design and implementation of code generators, translators, and optimizers at different levels of abstraction and across application domains, hardware targets, and execution environments. So let's just pause there. So we know LLVM works this way, that you have your LLVM IR, and then you basically write the front end of your compiler for the LLVM, and then LLVM does the back end part for your language. That's at least how I understand it. And then I guess MLIR tries to make this better, and that's what this is about. So let me bring the mic closer. One sec. Does this work? I hope so. Anyways, the contribution of this work includes discussion of MLIR as a research artifact built for extension and evolution, while identifying the challenges and opportunities posed by this novel design. Semantics, optimization, specification, system and engineering. 2. Evaluation of MLIR as a generalized infrastructure that reduces the cost of building compilers. Describing diverse use cases to show research and educational opportunities for future programming languages. Compilers, execution environments, and computer architectures. The paper also presents the rationale for MLIR, its original design principle, structures, and semantics. So as you see, we went through the introduction and then the contributions. Let's just read the last part of the introduction. The MLIR project aims to directly tackle these programming language design and implementation challenges by making it cheap to define and introduce new abstraction levels and provide in-the-box infrastructure to solve common compiler engineering problems. MLIR does this by 1. Standardizing the static single assignment SSA-based IR data structures, providing a declarative system for defining IR dialects, and 3. Providing a wide range of common infrastructure including documentation, parsing, and printing logic, location tracking, multi-threaded compilation support, path management, etc. This paper further presents the overarching principles underlying the design and implementation of MLIR. We will explore the essential design points of the system and how they relate to the overarching principle, sharing our experience applying MLIR to a number of compilation problems. So then we went to the contributions, then we learned about parsimony, traceability, and progressivity. And parsimony was apply Occam's razor to built-in semantics concepts and programming interfaces. Harness both intrinsic and incidental complexity by abstracting properties of operations and types. Specify invariance once, but verify correctness throughout. Query properties in the context of a given compilation with very little built-in. This opens the door to extensibility and customization. That's your parsimony. Basically, if I remember correctly, parsimony means how much you can customize something. And then you have traceability. Retain rather than recover information. Declare rules and properties to enable transformation rather than stepwise imperative specification. Extensibility comes with generic means to trace information, enforced by extensive verification. Composable abstractions stem from glassboxing their properties and separating their roles, type, control, data flow, etc. Progressivity. Premature lowering is the root of all evil. Beyond representation layers, allow multiple transformation paths that lower individual regions on demand together with abstraction independent principles and interfaces. This enables reuse across multiple domains. So proximity, it's premature lowering is the root of all evil. So lowering in this context probably means like going to the next level of your compilation. And then what premature is, I'm not sure about that. So beyond representation layers, allow multiple transformation paths that lower individual regions on demand. Together with abstraction independent principles and interfaces, this enables reuse across multiple domains. Alright. That's that. I guess we can read this once and then slingshot to the part viewer. Actually, I want to read this. I'm going to watch everything myself. So, I mean the videos. Where did MLIR? Yeah, we need to read this. Where did MLIR come from? Work on MLIR began with the realization that modern machine learning frameworks are composed of many different compilers, graph technology, and runtime systems, which did not share common infrastructure or design principles. This manifested in multiple user-visible ways, including poor error messages, failures in edge cases, and unpredictable performance, and difficulty generalizing the stack to support new hardware. We soon realized that the compiler industry as a whole has a similar problem. Existing systems like LLVM are very successful at unifying and integrating work across a range of different languages, but high-level languages often end up building their own high-level IR and reinventing the same kind of technology for high levels of abstraction. At the same time, the LLVM community struggled with the representation of parallel constructs. Okay, so parallelism, it's a important topic, it seems to be in MLIR. Of parallel constructs and how to share front-end lowering infrastructure. Example, for C calling conventions or cross-language features like OpenMP. What was OpenMP? OpenMP is an application programming interface that supports multi-platform shared memory multiprocessing So probably MP stands for multiprocessing programming in C, C++, and Fortran on many platforms. Instruction set architectures and operating systems, including Solaris, AIX, FreeBSD. Oh wow! So this is a very important thing that I didn't know about. OpenNPM is an application programming interface (API) that supports multi-platform shared memory multiprocessing. Who wrote this? Doesn't matter, I guess, because it's not here. On many platforms, instruction set architectures and operating systems, including Solaris, AIX, FreeBSD, HP, UX, Linux, macOS, and Windows. It consists of a set of compiler directives, library routines, and environment variables that influence runtime behavior. OpenNPM is managed by the nonprofit technology consortium OpenNP Architecture Review Board, jointly defined by a broad swath of leading computer hardware and software vendors, including ARM, AMD, IBM, Intel, Cray, HP, Fujitsu, NVIDIA, NEC. That's a cool building. NEC, Red Hat, Texas Instruments, and Oracle Corporation. OpenNP uses a portable, scalable model that gives programmers a simple and flexible interface for developing parallel applications for platforms ranging from the standard desktop computer to the supercomputer. An application built with the hybrid model of parallel programming can run on a computer cluster using both OpenMP and message passing interface, such that OpenMP is used for parallelism within a multi-core node, while MPI is used for... If you are not yawning enough, you are not learning enough. There have also been efforts to run OpenMP on software distributed shared memory systems, to translate OpenMP to MPI, message passing interface, and to extend OpenMP for non-shared systems. Alright, so let's take a look here. And is an illustration of multi-threading, where the primary thread forks off a number of threads which executes blocks of code in parallel. So you have a master thread, and then parallel task, and basically the master thread, probably this is highlighted, so it goes through these guys, but also the master thread only supports doing these guys, I think. Yeah. Alright, so that's that. Faced with this challenge, given we could not afford to implement any improved compiler instances, we decided to go for a more general solution, investing in a high quality infrastructure which would benefit multiple domains, progressively upgrading existing systems, making it easier to tackle pressing problems like heterogeneous compilation for specialized accelerators, and provide new research opportunities now that we gather a significant amount of experience building and deploying MLIR-based systems. We are able to look back on its rationale and design and discuss why this direction was pursued. Alright, so I guess you guys can go watch the first three videos. But that makes sense. I mean, we kind of understand the goal of the project, more or less, but not all the details. I feel like you need a lot of knowledge about LLVM itself and compilers to understand the low level of what these guys are doing. But let's just understand the high levels. So if we go to right here. An important aspect, okay, so we are into parallel compilation, which is a section of dialect specific, oh no, not here. Where's A to this? Okay, so we are in part 5, consequences of the MLIR design. The MLIR design facilitates the modeling of new language and compiler abstractions while reusing existing generic ones. Effectively, the solution to many problems is to add new operations, new types, possibly collected into a new dialect. This is a significant design shift for compiler engineering. It produces new opportunities, challenges, and insights. This section explores a few of them. Alright. And where were we? So we were in the consequences of MLIR design and we are here. So parallel compilation. An important aspect of MLIR is the possibility to use multi-core machines to increase the compilation speed. In particular, the isolated from above trait, section V8, section 5, VA, not 8, reusable compiler passes. Okay, the ability to represent multiple levels of abstraction in one IR incentivizes the passes that operate across these levels. MLIR handles extensibility by inverting the common approach. Since there are more ops than passes, it is easier for ops to know about passes. This also improves modularity as the dialect-specific logic is implemented within the dialects instead of the core transformation. Since the passes rarely need to know all aspects of an operation, MLIR relies on the following mechanism to implement generic passes. What are passes in compiler? Okay. It's fine. Pass is a complete traversal of the source program. Compiler has 2 passes to traverse the source program. Multi-pass compiler. Multi-pass compiler is used to process the source code of a program several times. In the first pass, compiler can read the source program, scan and extract the tokens, and store the result in an output file. In the second pass, compiler can read the output file produced by first pass. In the second pass, can read the output file produced by first pass, build the syntactic tree, and perform the syntactical analysis. The output of this phase is a file that contains the syntactical tree. In the third pass, compiler can read the output file produced by second pass. In the third pass, compiler can read the output file produced by second pass and check that the tree follows the rules of language or not. The output of semantic analysis phase is the annotated tree syntax. What about the abstract syntax tree? This pass is going on until the target output is produced. One pass compiler is used to traverse the program only once. The one pass compiler passes only once through the parts of each compilation unit. It translates each part into its final machine code. In the one pass compiler, when the line source is proceeded, it is scanned and token is extracted. Then the syntax of each line is analyzed and the tree structure is built. After the semantic part, the code is generated. The same process is repeated for each line of code until the entire program is compiled. Sure. Let's turn on. Oh, it's running. These guys know how to advertise. Anyways. Sure. Uh, 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 uh. Okay, so single pass is like this. You go lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generation, code optimization, code generator. But then in here you have your problems with single pass compiler. Okay, we cannot optimize very well due to the context of expressions are limited, as we can't back up and process it again. If the gain so grammar should be limited or simplified, command interpreters such as bash sh, tcsh can be considered single pass compilers, but they also execute entries as soon as they are processed. Two-pass compiler or multi-pass compiler, as a two-pass / multi-pass compiler is a type of compiler that processes the source code or abstract syntax tree of a program multiple times. A multi-pass compiler, we divide phases into two phases as first phase is your lexical analyzer, your syntax analyzer, then your semantic analyzer, then your intermediate code generator. But then you have your second pass. I mean, the other article said there are few passes, but this one is saying the second pass there's only two passes. First pass is referred as front end, analytic part, platform independent. And then second pass is your back end. It's your synthesis part. That's where you generate your assembly. And then last part is platform dependent. And it's also your backend is platform dependent. That's what LLVM does for you. And you don't have to write compilers for, I don't know, so many different architectures. Alright. So one pass compiler, it performs translation in one pass. It scans the entire file once. It generates intermediate code. It is faster than two pass compiler. Assembler. Why assembler? A loader is not required. No object program is written. Performs some processing of assembler directives. Data structures used are symbol table, literal table, token stream, and etc. These assemblers perform the whole conversion of assembly code to machine code is Mongo. Example: C and Pascal uses one pass compiler. Two pass compiler, it performs translation in two pass. It requires two passes to scan the source file. It does not generate intermediate code. It is slower than two pass assembler. A loader is required. A loader is required as the object code is generated. Platform processing of assembler directives not done in pass 1. Data structures used are symbol table, literal table, abstract syntax tree, intermediate code, etc. Data structures used are symbol table, literal table, abstract syntax tree. Oh, this one didn't use the abstract syntax tree? Interesting. Maybe it's in the etc, but it didn't say it right now, so maybe it is, but most likely it is not. These assemblers first process the assembly code and store values in the opcode table and symbol table, and then in the second step they generate the machine code using these tables. Module 2, what language is that? Niklas Werf. He's a Swiss computer scientist. This is interesting, guys. You learned something. Modulo 2. Okay, let's not go down this rabbit hole. Yeah, we were here. So, an important aspect of MLIR is the possibility to use multi-core machines to increase the compilation speed. In particular, the isolated from above trait allow ops such as functions to opt into the current IR traversal mechanism supported by MLIR's pass manager. Indeed, this trait guarantees that SSA use def chain cannot cross the region boundaries and can be processed in isolation. MLIR also does not feature whole module use def chains, but instead references global objects through symbol tables and defines constants as operations with attributes. Alright, okay, we take that. Let's move to interoperability. Interoperability. Our work involves interpretation, interpreter, interpretation with a large number of existing systems. Example, machine learning graphs encoded as protocol buffers, compiler IRs including LLVM IR, proprietary instruction sets, etc. Often the representation has a number of suboptimal or unfortunate decisions that made sense in the context of an existing system, but capabilities of MLIR enable a more expressive representation because importers and exporters are notoriously difficult to test. Test cases are often binary. We want to make sure the complexity is minimized. The solution is to define a dialect that corresponds to the foreign system as directly as possible. Allowing round tripping to and from that format is a simple and predictable way. Once the IR is imported into MLIR, it can be raised and lowered to a more convenient IR using all the MLIR infrastructure, which allows those informations to be tested similarly to all the other MLIR passes. There are numerous examples of such dialects, including the LLVM dialect, which maps LLVM IR into MLIR. This approach has worked well for us, and the MLIR tooling has also been useful to write tests for these foreign file formats. Section F. Unopinionated design provides new challenges. While MLIR allows one to define almost arbitrary abstractions, it provides very little guidance on what should be done, what works better or worse in practice. We now have some experience with a number of engineers and researchers applying the techniques and technologies to new problem domains and have realized that the art of compiler IR design and abstraction design is not well understood in the compiler and languages field. What? The art of compiler IR design, it's not known and well understood. Okay, maybe I can understand this. I give it a shot. I have no other choice. Many people work within the constraints of established systems, but relatively few have had the opportunity to define the abstractions themselves. This is a challenge, but is also another set of opportunities for future research. The broader MLIR community is building expertise with these abstraction design trade-offs, and we expect this to be a fertile area of study over time. Looking forward, the design of MLIR is different enough from other compiler infrastructure that we are still learning. Even after building and applying it to many different systems, we believe that there is still a lot to discover, as several years of research will be required to better understand the design points and establish best practices. For example, the rise of out-of-3 dialects increasing number of source language frontends using MLIR, possible application to abstract syntax trees, and applications to structured data like JSON. Possible abstraction to abstract syntax trees and abstractions to structured data like JSON. Protocol buffers, etc., which are still very early and what did I read? For example, the rise of out-of-tree dialects, increasing a number of source language frontends using MLIR, possible application to abstract syntax tree, and applications to structured data like JSON, protocol buffers, etc., which are still very early and are likely to uncover interesting new challenges and opportunities. Better support for just-in-time compilation and a precise garbage collection would also be interesting, leveraging the modularity and programmability of the IR. Section 6, related work. MLIR is a project that overlaps with multiple different domains, while the composed infrastructure provides a novel system. Individual components have analogs in the literature for references. The discussion directly related to the IR design itself, please refer to section 2. MLIR is a compiler infrastructure akin to LLVM, but where LLVM has been a great boon to scalar optimization and homogeneous compilation, MLIR aims to model a rich set of data structures and algorithms as first-class values and operations, including tensor algebra and algorithms, graph representations, as well as heterogeneous compilation. MLIR allows mix and match optimization, decomposing compilation passes into components, and redefining lowering cleanup roles. This is largely attributed to the pattern rewriting infrastructure, capturing full-fledged transformations as a composition of small local patterns and controlling which pattern rewrites are applied at the granularity of an individual operation, extending, formalizing, and verifying the rewriting logic automatically would be an important next step. On the backend side, MLIR's DDR has an analog to LLVM's instruction selection infrastructure, supporting extensible operations with multi-result patterns and a specification as constraints. Numerous programming languages and models tackle hardware heterogeneity. Originally a homogeneous programming model, OpenMD added support for offloading tasks and parallel regions to accelerators. Based on earlier proposals such as StarS's and Open Accelerated ACC, C++, AMP, HCC, and SciCL, leverage a conventional C-lang LLVM flow and modern C++ to provide a high-level abstraction for hardware acceleration. Unfortunately, all these programs very quickly lower high-level constructs to calls to a runtime execution environment, relying on pre-existing optimizations in the host language, typically C++. To alleviate the abstraction penalty, far fewer efforts target the heterogeneous compilation process itself. Alright, so what is homogeneous compiler? Alright, net library. Make this bigger. Yeah, this is fine. Alright, the definition of a heterogeneous computing environment depends to some extent on the application. Here we attempt a definition that is relevant to numerical software. The three main issues determining the classification are the hardware, the communication layer, and the software, operating system compiler, and compiler options. Any differences in these areas can potentially affect the behavior of the application. Specifically, the following conditions must be satisfied before a system can be considered homogeneous. The hardware of each processor guarantees the same storage representation at the same results for operations on floating point numbers. If floating point number is communicated between processors, the communication layer guarantees the exact transmittal of the floating point value. The software, operating system, compiler options on each processor also guarantees the same storage representation and the same results for operations on floating point numbers. We regard a homogeneous machine as one which satisfies condition 1, a homogeneous network, as a collection of homogeneous machines which additionally satisfies condition number 2. And finally, a homogeneous computing environment as a homogeneous network which satisfies condition 3. We can then make the obvious definition that a heterogeneous computing environment is one that is not homogeneous. The requirements for homogeneous computing environments are quite stringent and are frequently not met in networks or workstations or PCs, even when each computer in the network is the same model. Some areas of distinction are quite obvious, such as a difference in the, I didn't get any of that, but let's continue. Such as a difference in the architecture of two machines or the type of communication layer implemented. Communication issues are discussed in more details here. Some hardware and software issues, however, can potentially affect the behavior of the application and be difficult to diagnose. For example, the determination of machine parameters such as machine precision, overflow and underflow, or implementation of complex arithmetic such as complex division, or the handling of not the numbers and subnormal numbers could differ. Some of these subtleties may only become apparent when the arithmetic operations occur on the edge of range of representable numbers. Oh, maybe it's because I have my night shift. Anyways, to illustrate the potential problems, consider the iterative solution of a system of linear equations where the stopping criterion depends upon the value of some function f and the relative machine precision epsilon. The test of convergence might well include a test of the form this. So normalization of epsilon divided by normalization of x gives you, if it's less than f epsilon, then it's converged. In a heterogeneous setting, the value of f may be different on different processors, and ER and XR may depend upon data of different accuracies. Thus, one or more processors may converge in a fewer number of iterations. Indeed, the stopping criterion used by the most accurate processor may never be satisfied if it depends on data computed less accurately by other processors. If the code contains communication between processors within an iteration, it may not complete if one processor converges before the other. In a heterogeneous environment, the only way to guarantee termination is to have one processor make the convergence decision and broadcast that decision. Okay, let's go software engineering stack exchange. Maybe they give us something here. For me, the big advantage of heterogeneous abstract syntax tree is that it forms a kind of forced annotated switch statement, assuming a C-like language. For the homogeneous abstract syntax tree, you usually end up... Let's do this. No, we need it. Come on. Yes, better, a little bit. Anyways. Where were we? For the homogeneous abstract syntax tree, you usually end up the same kind of routine or class with a big switch statement. You need to keep track of which child node is what yourself. First child is the conditional, second First shell is the conditional, second the true block, third the false block. Whenever you change the code, you easily find yourself making a mental picture of your DSL syntax over and over again. Of course, you can document heavily, but a good program ought to be self-documenting as much as possible. The heterogeneous AST does just that. Furthermore, you can easily turn a heterogeneous AST into a homogeneous one, but not the other way around. Add the tag info, which is the good idea. Unless your language supports a cheap as a query, you can add node int index method to return the named field, so you lose nothing in generality by using the heterogeneous abstract syntax here. I won't mention what the heterogeneous AST is ideal for the visitor pattern, as it is just as easy to use the strategy pattern with the homogeneous switch routine. It is easier to add a specific functionality to the heterogeneous AST itself, though. If you want to turn into an interpreter, all you need to do is add some kind of eval methods. I would consider homogeneous abstract syntax tree if there are limiting circumstances. If you need to port the compiler to a system with no OOP language available, or if you need to optimize for speed, the homogeneous AST is easier to combine with FSM. What is FSM? Oh, finite state machine. The latter can also be an advantage if you want to have a general multi-purpose compiler that loads syntax rules on the fly. But it is easier to start out with a heterogeneous AST that will generate those tables after the compiler has been thoroughly tested. So all in all, I would say that neither tree offers specific advantages in terms of does this tree help or hinder in, say, semantic passes. The advantage of heterogeneous AST is, in my experience, to reduce the amount of thought and concentration you have to put into coding the tedious stuff of the compiler. There's a lot of repetitiveness and bookkeeping going on, so let the computer do the work for you as much as possible is my motto. Okay. Okay, let's read the post itself maybe. What are the reasons to choose a homogeneous versus a heterogeneous AST representation for implementing a complex domain-specific programming language? Just to be very clear about what I'm asking, here's some extra background. By homogeneous, I mean a tree constructed of nodes which are a single generic type. For example, I think this type is really language dependent. By using a C++ like struct for illustration, I consider this a minimal homogeneous abstract syntax node. So you have a node, you have your generic pointer, you have a tag, you have first child and the next sibling. So is it a binary tree? I don't know. By heterogeneous, I mean a tree constructed of nodes that are multiple individual types, one for each grammar production. For example, I don't want to assume a particular language, but again, using C++ like structs for illustration, I consider these types part of a hierarchy used to build a heterogeneous abstract syntax tree. So node, another node, a plus node, if a statement. Over the years, I've implemented several small special purpose compilers, usually in a very ad hoc way. I've never used much of a real abstract syntax tree because usually syntax direct translation has been good enough. Now I'm in the process of designing and implementing a new, much more complex language where I will building an AST and then walking over it with multiple passes for verification, semantic analysis, and so forth. For example, it seems that using a homogeneous scheme reduces the amount of code upfront, but I wonder if a heterogeneous scheme will pay off. Will pay off. Okay, so maybe so yeah, like an integer doesn't point to anything because it's the last level of branching in itself. But for if statement, you want the condition. So yeah, you want the condition, you want a then expression, you want a else expression. I feel like that's for his language. And but I wonder if a heterogeneous scheme will pay off better in the long run for reasons I'm not considering. On the other hand, the heterogeneous scheme seems like it allows benefiting from the compiler's static type checking. It allows benefiting from the compiler's static type checking, virtual method dispatch, etc. But I wonder if any of that is really very useful when developing semantic passes and so forth. Basically, I'm hoping to gain some insight from those who may have some real experience here. I've read many compiler books and have a moderate amount of basic compiler writing experience, but I haven't seen this particular dichotomy addressed in any literature I can get my hands on. Alright. Let's read this last part one more time. I would consider homogeneous abstract syntax tree if there are limiting circumstances. If you need to port the compiler to a system with no OOP language available, or if you need to optimize for speed. The homogeneous AST is easier to combine with an final state machine. The latter can also be an advantage if you want to have a general multi-purpose compiler that loads syntax rules on the fly, but it is easier to start out with a heterogeneous AST that will generate those tables after the compiler has been thoroughly tested. So all in all, but it is easier to start out with a heterogeneous AST that will generate those tables after the compiler has been thoroughly tested. So all in all, I would say that neither tree offers a specific advantage in terms of does this tree help or hinder in, say, semantics passes. The advantage of the heterogeneous AST is, in my experience, to reduce the amount of thought and construction you have to put into coding, like tedious stuff of the compiler. There is a lot of repetitiveness and bookkeeping going on. So let the computer do the work for you as much as possible. Alright, back to our paper. So now we know what running through passes is. It helps with your semantic analysis and syntax analysis, probably. Right? Am I right? Am I wrong? I don't know. This is... Okay. Where were we? Related work. Yes. For fewer efforts, target the heterogeneous compilation process itself. Parallel intermediate representations, extended LLVM-IR address part of the issue, but traditionally focus on the homogeneous setting. The most ambitious effort to date may be liquid metal, with a co-designed domain-specific language. DSL is domain-specific language. Domain-specific language. Anyways, a compilation flow converting managed object semantics into static, vector, or reconfigurable hardware. Yet most of the effort in its Lime compiler reside in fitting round objects into square hardware. Paraphrasing Kuh and Pallsberg, MLIR provides a direct embedding for high-level languages embracing heterogeneity through extensible set of operations and types, while providing common infrastructure for gradually lowering these constructs with maximal reuse of common components across the different targets. Tackling language heterogeneity has been a long-term promise of metaprogramming systems and of multi-stage programming in particular. Lightweight modular staging is a state-of-the-art framework and runtime code generator providing a library of core components for generating efficient code and embedding domain-specific language in Scala Delight. What is that? Scala Delight. Welcome. Alright, Delight is a research project from Stanford University's Pervasive Parallelism Laboratory. Delight is a compiler framework and runtime for parallel embedded domain-specific languages. Our goal is enable the rapid construction of high-performance, high productive domain-specific languages. Delight provides several facilities, built-in parallel execution patterns, optimizes for parallel code generation for Scala, C++, and CUDA, a heterogeneous runtime for executing domain-specific languages. Delight is being developed in collaboration with Programming Methods Laboratory, LAMP, at École Polytechnique Fédérale de Lausanne. Related projects include lightweight modular staging, Scala, Virtualize, and Forge. And Delight is still in alpha and there is no official release. However, the master branch should be relatively stable for experimental development of new DSLSs. For those interested in developing, so we are here. Their own DSLSs, we highly recommend using Forge, which is itself a DSL that automates much of the process of creating DSLs embedded in Scala. For those interested in using, instead of building DSLSs, alpha builds of OptiML, a DSL for machine learning, OptiQL. A DSL for data curing and OptiGraph, a DSL for graph analytics are currently available. Other unreleased DSLs may be found in the Forge GitHub repository and contact us if you have any questions. Publications. Okay, so this looks like they're not developing it anymore. But these guys pointed to it. So Delight promises dramatic productivity improvements for DSL developers while supporting parallel and heterogeneous execution. This approach is complementary to MLIR, providing higher level of abstraction to embedded DSLs and implemented optimizations through generic metaprogramming constructs. One step farther up into the language syntax, MLIR is among a class of parser generators that aim to facilitate the development of compiler frontends. MLIR currently does not have a general parser generator, no AST construction or modeling functionality. Combining MLIR with systems such as MLIR. Here we go. MLIR, another tool for language recognition, is a powerful parser generator for reading, processing, executing, or translating structured text or binary files. It's widely used to build languages, tools, and frameworks. For grammar, MLIR generates a parser that can build and walk parse trees. Okay, so Terence Pear is I feel like that's the person behind, the maniac behind MLIR. He's a tech lead at Google and until 2022 was a professor of data science and computer science at UNIV. Excuse me. Buck. Okay, we get it. MLIR is cool. It's a parser. It's a parser generator. What is the difference of parser engine? Alright, that aim to facilitate the development of compiler frontends. MLIR currently does not have a general parser generator, no AST construction, or that combining MLIR with a system such as MLIR could expand reusability upstream all the way to frontends and development environments. More narrowly construed by their application to machine learning, XLA, GLOW, and TVM address similar heterogeneous compilation objectives. These frameworks provide domain-specific code generation instances, starting from a graph abstraction and targeting multidimensional vector abstractions for accelerators. All of these could leverage MLIR as infrastructure, taking advantage of the common functionality while using their current code generation strategies. Similarly, the loop nest metaprogramming techniques from Halid and TVM and the learn TVM. What is TVM? TVM metaprogramming. Here we go. Apache TVM metaprogramming. Today we merged the PR, which added layout transfer as a T schedule primitive. The PR also includes a challenge in how buffers are loaded, stored, resulting in a massive change throughout the code base. If you are working on something that touches TIR, you probably need to rebase and resolve conflicts. Alright, and atomic flows such as polyimage, tensor comprehensions, stripe, Stripe, tensor compilation via the nested polyhedral model. Okay. Their underlying polyhedral compilation techniques could coexist as different code generation paths within an MLIR-based framework. This would greatly increase code reuse, defragmentation of the landscape, interoperability across domain, and portability. This is actually one of the motivations for the IREE project. Building on MLIR at multiple levels of abstractions, from tensor algebra and operator graphs down to the low-level orchestration of asynchronous coroutines of code generation for multiple CPU and GPU architectures within the Vulkan SPV standard. Finally, interoperability formats such as ONNX have a different approach towards addressing diversity of ML frontends by providing a common set of operations that different frameworks could map onto. ONNX would be a candidate as a dialect in MLIR, to and from which ops could be converted. We presented MLIR a concrete answer to the dual scientific and engineering challenge of designing a flexible and extensible infrastructure for compiler construction, ranging from backend code generation and orchestration of heterogeneous systems to graph-level modeling for machine learning and to the high-level language semantics of programming languages. and domain-specific frameworks. We demonstrated its applicability to a range of domains and discussing research implications. Motivated by the success of LLVM and looking ahead, we are eager to see how established communities in programming languages and high-performance computing, as well as domain experts, can benefit from the introduction of higher-level language-specific IRs. We also believe MLIR catalyzes new area of research as well as new approaches to teaching the art of compiler. It's an art. And IR design. Acknowledgements. This paper and project would not have been possible without the contribution of numerous other individuals. We express our gratitude to all. We also acknowledge the Google Visiting Researcher Program for supporting the third author at the early times of MLIR. Appendix. Abstract. The artifact of this paper includes the MLIR instruction, how to download and build it, and link to MLIR related source code in TensorFlow. Then you have the artifact checklist, so program MLIR, LLVM, C++ toolchain. Runtime environment, recommended Linux policy available, that this installation. You make dir that cd that cmake -g ninja LLVM DLLVM enable projects -d LLVM build examples on -d LLVM targets to build that -d cmake build type release that. All right. Yes, so I'm going to read the paper on how to write your own language in LLVM, and then I'm definitely going to come back for MLIR, and then we're gonna explore modular, the new programming language, and all of that. Wanna see what happens, you know. Yeah, but that's it for this video. I have to kind of meditate on all of this to let it sink in, and yeah, and I think from here to learning LLVM2 will be a good change already. So thanks for watching this video and see you in the next one.